basically it split the energy level, and it split the energy level in a well-defined way. It creates, instead of a continuous moving plane wave like these in the free electron case, it creates a standing wave. It has to be a standing wave because it anchors the wave go to zero at the boundary point, because it anchors it down. That's why you have a standing wave. It's not a traveling wave. The intensity must not be non-zero at the boundary. Okay, so that's the definition of standing wave. And you have this periodicity, the harmonics, so-called harmonic of this. So you have a sine function, right? This is a classic sine function. This is half a sine function, and so forth. And it all depends on the quantum number you have. So you have different standing waves, and also the energy level is quantized, and is quantized in a well-defined way. And in this case, the energy is proportional to the n squared, where n is the quantum numbers of this. So we go very, very beautifully. It's sort of 1, 4, 9, 16, and 25, and so forth, depending on what the n integer n values are. Is an indigo of these numbers. Okay, so the effect of boundary condition is quantization of the energy level and creating of standing wave. So last day we were looking at these. What happened if you add an additional well next to it? So here you have a let's look at this one. You have this double square well problem. So it's a one square well. You have two. So you have, think of this one well and then the second well, and outside the well you would have 0. So there you can actually divide this into 5 regions. You have 2 regions outside the infinite well wall, okay, and then you have this region 2 and region 3 inside the individual well on each of the other side, and then you have a connecting point, this barrier between the well, and this is where the interesting thing occurs, is that you have an energy barrier between the 2 square wells. So you can imagine this sort of simulate a hydrogen molecule, right? Because you can think about that if you have an iron core inside here and here, and in between you have some barrier to move the electron from one iron core to the other side of to the other atom, hydrogen atom, like this. So it's very similar to hydrogen molecule. By putting this square well side by side, is a qualitative approximation of the hydrogen atom. Okay, and you can see why we are doing this, because if we can do this 2 square well, we can probably do 3 or 4 and 5 and so forth on. We can extend our the number of our square well to multiple square well, and that, what does it get us? It gets us a linear chain with periodicity, right, in this direction, and that's a simulation of of the material, of the crystal, emergent of a one-dimensional crystal if you simulate it like this. Okay, so you can define these square well potential, right? Again, the potential is infinite on outside the 2 well, and inside the well is 0 again, and then in between the well, where the potential, we just set it arbitrary to some V naught value, and V naught correspond to my barrier, and so I can tune this barrier height to whatever I want to stimulate some condition, some molecule, and so forth. Okay. So that's the basic logistic, and I don't want to go into too much detail because it involves a little bit more math than the single square well problem. But the logistic, I just want to see you, let you see the strategy, if you like, of solving a problem like this. So you have, so usually you always define your potential. So you define the potential in the different regions. So this is outside the double square well region. The potential is infinite. Between the well, that's the barrier. So you have V naught, and inside individual well you have 0. So that's the first task. Second task is that you write down the equation of motion, which in this case is a differential equation. So you have some operator operating on some function, right? That's the kinetic energy terms. And then you have another operator, which is the potential energy term, which is defined by this, right? So this is V of x is in fact this whole bit here in different regions. So there are different chunks of potential on that. And finally, you have the energy, which is what you're after. So what you're trying to solve for are the energy and the solution, which is the wave function that give you that energy. Okay. So so here we say that, well, okay, let's we can do this in chunk, right? So we can define different region and solve for this equation in different part of the potential. So let's look at inside the square well, right? 2 and 3, they should be very symmetrical, and it's easier because here in 2 and 3, the potential is 0. So it look like we are just look like again like the single square well problem, right? And you should have one gets this linear combination of 2 plane waves, right, going in different directions, right? You can tune your A and B constant to get whatever you want, okay? And then the action region is really the most interesting region, is the barrier height region, right, where between the square well in this region here, and there you have this finite constant value in the potential, this V naught. And so in order to simplify the math, people often rewrite V naught as some constant, this constant h bar squared divided by 2m, and again, h bar, I remind you, h bar is just a constant, Planck's constant, divided by 2 pi is a shorthand notation for the quantum mechanic people to solve this problem. And the reason why you write that, because you see, you have h bar squared divided by 2m in your kinetic energy terms here, and if you can rewrite your V naught in this, think of h bar divided by 2, big bar squared divided by 2m as the unit, right? And then so everything is in the same unit. So it may simplify our life a little bit easier if you rewrite it. It will not change anything inside, but it just make it a little bit easier to solve. So you rewrite this in this way. What you got is that, and you put in wave functions, right? So the effect, this alpha here, alpha square, is kind of this whole term in green is a constant, right? And this energy term is supposed to be a constant as well. So in effect, you can think of this as really like this, except that energy term, your total energy has been changed by this barrier height. So it's a modified energy term that you got there. So that's what I want you to see. That's just the logistic in solving without really going into the more detail. So when you do that, then you would expect that this wave function also probably should have the same form, right? Same form as the wave function in the well. So it's a linear combination of 2 plane waves. So these are the plane waves, except probably your wave vector has been modified due to this barrier height, this alpha here. So k here corresponds to E. So or rather k squared corresponds to E, right? Because E is proportional to the momentum divided by 2m, and the momentum is proportional to h bar divided by 2 h bar times k, right? That's the momentum. So energy, the kinetic energy should be proportional to k squared. So you can think of this as a k squared minus alpha squared here due to the